All right, guys, we're going to move on from systems of equations, which you're probably happy to hear. We're going to move on to some graphs. So in this first section, we're just going to start with some qualitative graphs. We're going to review independent and dependent variables, which you've seen many times before. Look at features of a qualitative graph, including the rates of change, x and y intercepts. Again, these are things you've seen many times. Decide whether that graph is discrete or continuous. This you might not be as familiar with. We'll talk about that. We're going to draw a qualitative graph from a context, and then given a graph, interpret the context of that. And then we're also going to distinguish between linear change and nonlinear change. These are things you might have seen a little bit in the past. All right, so let's take a look at this first example. What's the real world meaning of this kind of very simple graph? What does the slope represent? What is the meaning of the intercepts, and is it a linear relationship? So this graph shows the relationship between the number of customers getting haircuts each week and the price charged for each haircut. Let's start off with the easiest question. Is this a linear relationship? Well, hopefully you can see that yes, it is, because we have a straight line, right? Which means there's a constant rate of change. What does the slope represent if we go back up to that beginning question? So remember, slope is going to be change in y over change in x, delta y over delta x. So what is our y variable? It's the number of customers each week on that y-axis. And then our x variable is the price of a haircut. So our slope looks like it represents the number of the change in the number of customers each week, depending on how I change the price of my haircut. Right? So that'll make a little more sense if we look at this graph and interpret maybe some points on the graph. So what I mean by that is if I charge a lot for a haircut, that means I'm going to get fewer customers, right? If I have a ridiculously expensive price for haircuts, not a lot of people are going to come in. As I start to charge less for a haircut, so if I have a haircut that is more reasonable, I'm also going to get more customers, right? So if my haircuts are a reasonable price, more customers are going to come in. That makes sense. So my slope is going to represent what I gain, maybe what I gain in the number of customers, depending on how much I decrease the price of my haircut, would be a way to interpret that. All right, so what is the meaning of the intercept? So intercepts are going to be, right, your y-intercept right here. Let's start with that one. What's the meaning of that y-intercept? So it looks like that's the greatest number of customers that are coming in according to this very low price for a haircut. So if I'm giving free haircuts, I'm going to get tons of customers. If I don't charge anybody and I just say everybody come in for a haircut for free, I'm going to get lots of customers. So this maybe is, I don't know, we could say it's a free haircut. So in other words, at $0, I'm going to get a ton of people, right? Hoping that I give good haircuts, I suppose. And then my x-intercept, so it's my y-intercept. If I look at my x-intercept, it looks like I have 0 customers. So my y is 0 because I'm charging a lot for a haircut. So here my price is $0 at my y-intercept, and my x-intercept I have 0 customers. Again, why? Because I'm charging too much for a haircut. So that's what my x and y-intercepts mean in this case. Okay. So now, well, actually, we're going to skip that because I think we've talked about all that already. Let's look at an example. Students at, this is Central High School, let's go with students at Holy Angels, are complaining that the juice vending machine is frequently empty. Several student council members decide to study this problem. They record the number of cans in the machine at various times during a school day, and they make a graph, and that graph is down here at the bottom. All right, so let's take a look at some of these questions. Based on that graph, at what times is juice consumed most rapidly? So when I'm looking for this rapid consumption of juice, what type of slope am I looking for? I should be looking for a very steep slope. If I'm looking for something that's happening very, very quickly on a time graph, I'm going to have a very steep slope. So what times is juice consumed most rapidly if I'm looking at the steepest slope? Not only steep, I guess I should say, this should be a positive slope as well. if I look at my graph, this will make sense. So it looks like I have a very steep and positive slope right here. Right, so does this make sense that juice is being consumed very rapidly right here? So this is what about, so I have my times down here. It looks like that's close to 12:30. And in very little time, so by about 12:45, so in only 15 minutes, my machine has gone from empty, or sorry, whoop. You know what? I was looking at that backwards. I was looking at that as being full. So let's do that again. One more time. All right, so let's take a look at this point to this point right here. Again, very, very steep slope, but don't make the same mistake I did. The top is full. The bottom of my y-axis here is empty. So this should make more sense. So starting at about 11, we'll say what, 11:15? And again, in a very short amount of time, by about 12:15 there at the bottom, I have this rapid consumption, right? The machine was full up here. And then in the next half hour, the machine is all the way empty. So that's a pretty rapid consumption. So now is there another point where I see this rapid consumption? So it's a steep slope, and it's also a negative slope. So I said positive a minute ago. This is negative. Again, don't make the same mistake I did. Full is up here, empty is down here. So this is also a negative slope. So is there another very steep and negative slope? Well, I could take a look at this point to this point right here, right? Again, about the same steepness. So this goes from about 3 o'clock to about 3:30. So within just a half an hour, again, that's a very quick consumption of juice. And that goes, it wasn't full, that's about 75% full down to empty. So again, that's another rapid consumption. So those are the two times where we would say juice is being consumed most rapidly. Whoops. All right. So let's take a look at the next question. When is the machine refilled? So we're looking from empty to full, right? Well, it makes sense that we would say, you know, here's nighttime, and then in the morning, that machine is full again. So it looks like it's filled overnight. So we have overnight. And then are there other times when it goes from empty to full? So it looks like from empty here to full up here. So at about 4 o'clock. We could say that's probably at the end of the day when all the students leave, it's refilled again. Or when a lot of the students leave, maybe it's refilled again. Some stay and consume more cans, right? But it's refilled again at 4 o'clock at the end of the school day. Is it refilled to its fullest at any other point? It's not refilled up to the top at any other point, completely from empty to full, but it looks like it's also refilled from about less than half full to full at this point. So at about 10:15 a.m. it's also filled. And then it looks like we go from empty to about 75% full at that point. So from about 12:15, it's filled up to about the 75% mark. So anytime I'm seeing a positive slope, that's being refilled. Let's see, when is the machine empty? Well, hopefully this is an easy one. We can see that the machine is empty when it's down there at the bottom at about 12:15, and then at about 3:30. That machine is empty, and we can see that because it's all the way down at the bottom of the graph, right? So we have empty here. We have empty from here to here, right? So from about 3:30 to 4, it's empty as well. So what do you think the student council is going to recommend to solve the problem? So I want you to answer that for yourself. Now, something else I want us to consider about both of these examples that we've done so far, the haircuts and also the juice machine, is that should these actually be represented as continuous graphs? So those were continuous graphs. In other words, all points were connected, right? In the haircut, we have a continuous graph. It's a continuous line. And the other one, you know, it was going up and down, but it was still continuous. All points along that line are included. So those are continuous graphs, or it's like we're connecting the dots with continuous graphs. But should we actually be connecting the dots in those two graphs? So make sure to write this down. Discrete graphs represent values at specific points along the number line. These two scenarios that we've done so far should actually be represented with discrete graphs. For example, the quantity of juice cans in a machine and the number of haircuts can only be represented with whole numbers. I'm not going to say that I have 1.5 cans of juice left in the machine or 15.75 cans of juice left in the machine. I can't do that. So I really shouldn't be connecting all points on the graph. These should be represented at specific values. And we'll see this in the graph on the right in a moment. The price of a haircut also, if I think about that first graph, can only be represented at specific values or at specific prices. If I say a haircut is $20, I'm not going to charge $20.75 for a different person. So there's specific values or specific prices for the haircut. So when the values on your graph or in whatever scenario you're talking about can only be specific values, sometimes those are only whole numbers, okay? But sometimes you're also going to include decimals or fractions, but they have to be very specific values. So if you look at the graph on the right, this is a good example of how this would look. So this is the juice cans again, same graph we were looking at a minute ago. But this is a discrete graph. So how would we read this? So we could say at, let's take a look right here. So we could say at 7 in the morning until somewhere around 7:15, there are a specific number of cans in that machine. Right, so let's just go by, so we're starting at empty down here, so let's just go by tens. We'll say 10, 20, 30, 40, 50. So at that time in the morning, there are 60 cans of juice in the machine. Right, I'm not going to say that there could be 57.35 cans. It doesn't make sense. It's got to be that whole number. So now if I look at, let's take a look at this one. So it looks like from about 8 a.m. to 8:45 a.m. Again, there's a very specific number of cans in that machine. There might be exactly 35 cans in the machine. I can't have a part of a can. So last thing about this, when I jump from, so right here, at 8:45 a.m., there are 35 cans. When I go down to that next value, so this again is at 8:45 a.m., right? The time hasn't changed, same value on my y-axis, I jump down to 30 cans. Right, so those values on a discrete graph are going to jump from one value down to another value in a very, well, in this case, 8:45, again to 8:45. Why is one of those, so let's get rid of that again. So why is one of those values, or why, it keeps moving on me. Why is one of these filled and one unfilled? So take a moment and think about why one of those might be filled in, those circles, and why one of those points might be an unfilled or an open circle. Think about what you know about graphing inequalities on a number line. When a circle is filled in, it's going to be equal to, right? When it's an open circle, It's not equal to. A solution doesn't belong there. So with a filled circle, that's where I'm saying at 8:45 there are 35 cans, right? And then I'm going to jump down to that next filled circle and say at 8:45, so at the next moment, I only have 30 cans, right? So right here, in other words, my unfilled circle means that that's where I jump down to my next value. All right, I know that got a little confusing. So my unfilled circle is where I jump down to the next point. So I go from 35 cans to 30 cans at that unfilled circle. Now we looked at two examples that technically should have been discrete graphs, but oftentimes with discrete graphs, it's easier to see a pattern if you represent those with continuous graphs. So for the haircut and the juice can problem, we originally saw those with continuous lines because that gives us a good indication of the pattern. So it's easier to see the pattern of what's happening, especially in a time graph, when they are continuous, even though sometimes those contexts really should be represented discretely. So do all stories give continuous graphs? No, hopefully you saw that in the juice cans and the haircuts. Those should be continuous graphs. But again, sometimes it's easier to see the pattern if you represent those graphs or those scenarios continuously.